So what I wanted to do today is continue talking about fault tolerance, and as a consequence of the Easton-Nil theorem, which I just reminded you of, we can't get a universal set of gates with just transversal things. So we're going to have to do more. And moreover, there's more parts to a fault-tolerant protocol than just doing gates, right? We have to prepare. We need all sorts of different locations. So in particular, the way we imagine a fault-tolerant protocol to work, and basically all the fault-tolerant protocols that have been devised so far work in this way, is we'll start with some circuit that we would like to implement. So it'll consist of various different kinds of locations. Remember, preparation locations, gate locations, measurement locations. And what we're going to do is we're going to take that circuit and convert it into a fault-tolerant version of the circuit by taking each of the locations in the original circuit and turning it into some fault-tolerant thing, which is called a gadget. So for instance, we'll have state preparation gadget, and this state preparation gadget will be some more complicated thing. It may involve control NOT gates and more state preparation, certainly maybe some measurements as well, and could be classical control based on those measurements, things like that. Okay, and this will correspond to one location. All of this, which could be very simple or could be very complicated, will correspond to one location in the original ideal circuit. Okay, and so we're going to have a bunch of these things. And put them together. And then we're going to intersperse these with error correction steps. Okay? And the error correction steps themselves could be fault tolerant, right? We shouldn't, while we're attempting to correct errors, we don't want a single fault to ruin our computation. So we're going to have to be careful how we design those as well. And so each of these things is called a gadget. And so there'll be state preparation gadgets, there'll be gate gadgets for all the different kinds of gates, there'll be measurement gadgets, and there'll be error correction gadgets. Okay? And so far I've shown you gate gadgets that are implemented using transversal gates. Right? That's a simple example of a gadget. You take, say, the Hadamard gate for the 7-qubit code, and you implement the logical Hadamard by performing the physical Hadamard on each of the 7 qubits of the code. Yeah?
So one more time, gadget is not fault tolerant, right?
Well, a gadget is not inherently fault tolerant, right? Just because you're implementing your logical gate using some more complicated system, that may be a bad way of doing it, right? It may not work. So I'm going to define in just a few minutes what it actually means for a gadget to be fault tolerant. Yeah, so the reason we do this is because, if you have some really big complicated circuit, well, sure, there may be some totally different big complicated circuit, bigger and more complicated, that will do the same thing in a fault-tolerant way. But we don't really know how to do that, right? That could be a very complicated transformation. Instead, what we'd like to do is take it kind of piece by piece. And this way, you can have a circuit of 100 million gates, but there's only 5 different kinds of fundamental gates that it's built out of. And so if we have a gadget for each of those 5 fundamental gates, then we can put them together to make a fault-tolerant circuit for this whole giant circuit. Okay? So what it does is it kind of keeps the size of the fault-tolerant protocol specification under control. We only have to think of a couple of different things. In this case, in that example, 5 things. Okay? Any other questions? Okay, so when I'm defining these things, I'm going to use some sort of graphical notation, and so I'm going to use something that looks like this for a state preparation gadget or location. Okay, maybe I can use a different color. So I'm going to, for the, well, okay, and I'll use boxes, square boxes. Well, sorry. Let's do it the other way. So let's use, I'm going to use circles and ovals for gate locations or gadgets. And I'm going to use semicircles in the other direction for measurements. And then I'm going to use boxes that say EC in them for error correction gadgets. And so the other thing I'm going to do is I want to distinguish in these definitions between encoded qubits, which are actually blocks of an error correcting code. So yeah, which are blocks of an error correcting code, and those I'll use with thick white lines. And unencoded qubits, which are going to be thin purple lines. And so the assumption here is that the encoded qubits are implemented using a quantum error correcting code, and you can have errors on the physical qubits making up the encoded qubits. But when I'm talking about unencoded qubits, I'm living in the ideal world where the unencoded qubits don't have anything bad happen to them. They do what they're supposed to do. Okay. So for instance, if I use thin purple lines to draw one of these gate gadgets, that gate will act correctly. Okay. Let me do the definitions, and then you'll see. So the point is that I want to say for each gadget what it means to be fault tolerant, for that gadget to be fault tolerant. Okay, and I'm going to do that by relating the behavior of the fault tolerant gadget with physical qubits having errors to the ideal behavior. Okay, so maybe that's the answer to your question. Okay, so I guess the other thing I wanted to comment is that I'm going to present this for the case like the 7-qubit code where you're encoding one logical qubit in a single block of the code. But really, that's not essential for any of these definitions. It modifies things slightly if you have a code that encodes multiple qubits per block, but it's not in any really important way. Okay, so to do these definitions, I'm going to need two basic notions. Okay, so I have a qubit encoded in an error correcting code, and I want to say things like this code block has no errors on it, or it has one error or two errors. So how do I define that rigorously, right? In the general case, you're just given a quantum state. What does it mean to say that this has 0 errors or 1 error or 2 error? You don't even know what the state is supposed to be. Okay? But you do know that it's supposed to be a code word of the quantum error correcting code. So that's what we can do. We can define the number of errors as relative to some code word. So we do this with what's called an R filter, which graphically I'll denote this way as a thin rectangle with an R on it. And this represents a projector I need space here, onto the subspace of the quantum error correcting code with less than or equal to R errors. And it's enough to think about Pauli errors by the theorem I showed you on Tuesday. So what do I mean precisely by that? I mean, so the 0 filter then is the projector onto the code subspace, and the 1 filter is the projector onto the subspace spanned by the states of the quantum error correcting code with a single Pauli error on them. But it's a subspace, so it could also be a sum of states of that form. Okay? And similarly, the 2 filter is the projector onto the subspace of the code states with 1 or 2 Pauli errors and superpositions. Okay? And so a state that passes through this R filter unchanged, we kind of intuitively means that it has only R errors on it. Okay? Now a state that has more errors, you can still put it through the R filter, but part of it will get projected out, so it won't be the same anymore. And for these definitions, I'm only really going to care about equality. So that's what you can think about that way. Okay, so the next definition I need is when we talk about a quantum error correcting code, we want to say what is the encoded state? What is the state that's currently the logical state of the qubit? And again, you don't know what it's supposed to be, so this is not a presumption about whether the state is right or wrong. We just want to know what it is. How do we talk about this? And in the case where there's no errors on it, that's pretty obvious what you do. You just say, oh, well, I'll decode the state and see what it is. Well, I won't necessarily see what it is. I won't look at it. But I'll have a qubit there. And that will be the logical state. What about when there are errors? Well, what we should do then is we should apply some error correction procedure and then decode it, right? Get rid of the errors and see what the logical state is then. But of course, if you did this in the real world, the error correction procedure itself might have errors, and that would mess up what you're doing. But we're not talking about the real world here. We just want to say conceptually, what is the state that's encoded? We're not actually decoding it. So what we're going to do is we're going to have an ideal decoder. And graphically, that's going to be represented by this. We have a thick line. Where's my purple? There. And kind of a triangle, and then a thin purple line. And that tells us we're going from this encoded state to this unencoded state that doesn't have any errors. Okay? And again, this is a conceptual thing, not something you can really do, but this is kind of the definition of what the encoded state is, the logical state is, at any given point in the computation. Okay? So there are questions on those things.
Does triangle imply measurement or anything?
Yeah, I guess it's a little hard to see the difference between the purple and the white now I look at it. But okay, hopefully you can still see thick versus thin. Is that okay? I can still change colors at this point. Okay, so yeah, it doesn't necessarily imply anything about measurement. First of all, again, this is an ideal thing. So and it's not something we're really doing. So any measurements we make should not be kind of messing us up. But if you want, you can think about it in measuring the error syndrome. That's acceptable. In practice, probably you want to do the whole thing in a unitary way, so you're not even measuring the error syndrome. That can be done. I didn't discuss that. But the thing is that it is kind of a non-unitary operation because the way I've described it, we're taking in a whole code block with say 7 qubits, and we're getting out only 1 qubit. Okay, so we're throwing away some qubits. Again, you can kind of purify it and take the unitary that keeps track of those extra qubits, and that's useful for technical reasons, which I won't get into. But sure, if you want to think about measuring the error syndrome there, that's fine. Any other questions? Okay, so given these tools, what does it mean for gate gadget to be fault tolerant? So it has to satisfy two properties. So we have the so this is the gate propagation property. The GPP. And the GPP says that if we're given, so all of this is going to be for code that corrects T errors. So if we're given a state that comes in that passes through an R filter, oh, sorry, wrong one. And then we do a gate gadget that has at most S faults, then what I want to say is that a state in this situation shouldn't accumulate too many extra errors. The state that comes out, so we started with R errors, we had S faults, and I want to say that the state that comes out has at most R plus S errors. And so the way that I do that is I say that this thing here is equal to this. Okay, so this is saying that this thing here, where we have an R filter and then S gate errors, so is equal to itself if you stick on a projector, a filter for R plus S errors. Okay, so that's what I mean by saying that this has the output state here has at most R plus S errors. Okay. And this should apply when R plus S is less than or equal to T. Okay? Does that make sense? Now, I also want to do this for gates that have that involve two blocks. Like the transversal C0 gate involves two blocks of the 7-qubit code. So how is it going to look then? Well, now we have two blocks coming in, and the first one has R1 errors, the second one has R2. Then we do the gate, it has S errors. And these states at the end, sorry, this is the left-hand side. So this should be equal to the same thing, but with some filters on the end. And so the question is, what should these filters be? And we're going to assume here that R1 plus R2 plus S is less than or equal to T. So clearly, well, OK. So obviously, we're going to have an S in here, because any errors that occur during this gate gadget could affect both blocks. But it's also the case, remember, that the C0, for instance, or really any non-trivial 2-qubit gate, can propagate errors from one block to the other block, right? And so we have to allow that if we want to be able to find gates that satisfy this definition, gadgets that satisfy this definition. So we're going to allow the accumulation of errors from here and from here up into the top block. So this is going to be R1 plus R2 plus S. And down here it's also R1 plus R2 plus S. And remember, this is OK, because when we assume that R1 plus R2 plus S is less than or equal to T, assuming that we have this situation, then each block of the code is able to correct the error that we still have. So it's worth saying that this assumption that R plus S is less than or equal to T, it might still be true that these equations might still be true even if that assumption is not satisfied. So for instance, for transversal gates, these things are always true just by the structure of the transversal gates. But for more general gate constructions, we only want to insist that these have to be true when this is satisfied. Okay? Don't have enough room here. Okay. Okay, so that was one of the conditions. So the other condition is the GCP, the gate correctness property. Let's do this. So the gate correctness property, so the gate propagation property was telling us that errors don't spread too fast, that we have the control of error propagation in these gadgets. The gate correctness property is going to tell us that the gate gadget does what it's supposed to do on the logical gate. Okay, obviously that's important, right? And so again, we're going to do this with the assumption that there's not too many errors in here. So we're going to have to do that by saying that the incoming state has at most R errors. It passes an R filter. And then we have the gate gadget that has at most S faults. And we're going to again assume here that R plus S is less than or equal to T. And we're going to follow this by an ideal decoder. Okay? And so this is saying we're going to do this gadget and then see what the logical state is afterwards. And that should be equal to this, where we have the R filter and then we immediately do a logical decoder. And then we do the gate. Okay? So what I'm saying is that the logical state after the gate gadget is the same as the logical state before the gate gadget with the ideal gate performed on it. Okay? Does everyone understand how that captures the notion that the gate gadget is doing the right thing? So in this case, I had to put this this R filter in front, even on the right-hand side, because I want this to be, these diagrams represent actually general CP maps. And I want this to be true as an equality of CP maps. So that means that it really could be any state that's coming in here, right? And then I'm going to project out the part of that state that has only R errors. And so I have to do that on the right-hand side too, because the part that has more than R errors, this might not work. Okay? This is really just ensuring that you have the same input on the left and the right, and that it satisfies this condition. Okay?
Where are S errors on the right?
That's right. So the S errors on the right are gone. Right? I'm saying that when we push this ideal decoder back through, there are no more errors. So this should be true. This equality, my claim is that this equality is true no matter what S errors occur here. Right? And that's really kind of critical part of fault tolerance, right? That the logical state should be doing the right thing no matter what errors occur in the system, provided there aren't too many. Yeah?
So this gate with errors, should I think of it as like a perfect gate and then some like random composed with some like random polys?
Yeah, generally that's a reasonable way to think about it. If you think of like this is a transversal gate, so suppose we're doing the Hadamard on all 7 qubits. Then one way to think about it is, say S is 1, then you could say, well, 6 of the Hadamards are right, and 1 of them you do the Hadamard and then a poly. Or you could do a poly and then a Hadamard. Or, and this is completely consistent with notation, you just replace the Hadamard with something else altogether on that one qubit. And those are all they're not exactly equivalent, but up to the ability of the quantum error correcting code, they're the same, because the error correcting code will correct any single qubit error. Yeah?
Do we assume some sort of error correction in the IDR decoder, like measuring?
Yeah, absolutely. So, so this is a code that corrects T errors, and this ideal decoder just runs the kind of the perfect error correction procedure on this code as part of the decoding. So that's why this can work, right? Because this is saying, well, we have some errors here, but then this ideal decoder will get rid of them and just extract the logical qubit. And here, the ideal decoder gets rid of these pre-existing errors and then does the thing.
So it's like we run the entire decoding unitary circuit and then measure these auxiliary qubits and then...
Yeah, that's right. That's right. That's one way of doing it, yeah. Okay? Yeah?
So just to be clear, the left-hand side, I guess the gate is acting on the encoded qubit, so it has to be like transversal acting on that whole block.
Well, it'll be some fault-tolerant gadget, but transversal was an example. That's right.
The right-hand side is just acting on a single.
That's right. That's right. And I mean, I know it's hard to tell, but this one I drew in purple.
Oh, I see.
Here, let me fill this in to make it more obvious. Okay. So, so of course, there's also a 2-qubit, 2-block version of this, which I'm going to try to squeeze in down here. So again, we have R1, R2, the gate with S. And then we do ideal decoders on both of them. And then on the right-hand side, we do the decoders right away. Then we do the ideal gate, and it should be the same. And again, this should apply when R1 plus R2 plus S is less than or equal to T. Okay? And of course, if you have kind of a 3-block gate gadget in your fault-tolerant protocol, then you can generalize this in the most obvious way to 3 blocks. Okay? Okay, so let me quickly go through the definitions for other kinds of locations. So we'll also have preparation locations and measurement locations. And then we're going to have to talk about error correction gadgets. And they're all kind of slightly different, but very similar in concept to these, with one real exception for the error correction gadget. So for state preparation, we have the PPP, the preparation propagation property. And that says that, so we have so for the state preparation, there's no pre-existing errors. We're starting with nothing, and we want to get a logical qubit. And so what that's saying is that if our preparation procedure has at most S faults in it, then that should be equal to this situation where we have a filter afterwards. So this is saying that if there's most S faults in the preparation procedure, then the output state has at most S errors. And we assume here that S is less than or equal to T. And then we have the PCP, the preparation correctness property, which is saying that that the prepared state is what it's supposed to be. And so that's saying if we take the state preparation gadget, we do an ideal decoder, then that's equivalent to just doing the ideal state preparation. Okay? And so then for measurement gadget, there's no propagation property, right? The propagation properties say how many errors we have on the output state. But a measurement has no output state, just classical bits, which I should say we're assuming are perfect. So we only have a measurement correctness property. And that says that if we have a state that passes an R filter, we have a measurement procedure with at most S faults. Sorry, that's supposed to be an equals. Then that's equivalent to taking this state that has R errors and then decoding it and doing an ideal measurement. Again, with R plus S less than or equal to T. Okay? So the point is that the measurement gadget is going to do some measurement on the encoded state and then will involve some decoding into, say, a single classical bit, right? And the point is that we get the same classical bit, or at least the same distribution of classical bits and the same conditionalizing on the rest of the state that we would have if we had decoded with an ideal decoder and then immediately measured it. Okay? Does that make sense? Okay. And so then we have to talk about the properties for the error correction gadgets. So we have the ECRP, which is a little bit different. This is error correction recovery property. And so this is going to look a lot like one of these propagation properties, but with one difference. So the ECRP says that if we have an EC step with S errors, S faults in it, then the output state should pass an S filter. And here we're going to assume that S is less than or equal to T. So the way this differs from the propagation properties, there's no assumption on the input state. It doesn't have to pass an R filter. And the reason for that is the error correction is supposed to get rid of those pre-existing errors, right? So this property by itself is not saying anything about whether the state that comes out, the logical state, is correct or not. That's going to be the correctness property. This is just saying that if you give it some totally random state and apply this error correction procedure, if there's not too many errors, in the case where there's no faults in the error correction procedure, the state that comes out should be a valid code word, right? Of course, if there were lots of errors, it won't be the code word that you wanted, or it won't necessarily be the code word that you wanted. That can't be helped if that happens, but it should be a valid code word. And similarly, this is a stronger property than that because it says that even if there's S faults, where S is not too large, during the error correction procedure itself, the state that comes out should have no more than S. Now, we can't avoid having this filter here, right? Because those S faults could happen right at the end of this error correction gadget. So we can't expect the error correction gadget to correct errors that occurred during the gadget. I mean, it might. If you're lucky, they happen early and you're still going to correct that type of error later. But you can't count on it. Okay? But we want to say that single faults during this error correction gadget don't blow up to create many errors in the code. And so that's what this property is saying. Well, that's part of what this property is saying. Okay? And then we have the ECCP, the error correction correctness property. And that says, so in this case, we do want to make the assumption that there's not too many errors coming in because we can't expect to get the right logical state without that assumption. Saying if you have an R filter and then an error correction step with at most S faults, and then you do an ideal decoder, then that's equivalent to doing the ideal decoder right away. And notice in this case, I don't need to put the kind of ideal error correction because the ideal state doesn't have any error correcting code. It doesn't have errors. Okay, this is just saying that the error correction procedure doesn't change the logical state in the situation where you don't have too many errors. Okay? Yeah.
Shouldn't S be smaller than R?
No, we don't need that assumption. So in particular, if you have a code, even if you have a code that corrects just one error, you definitely want this to work in the case where there's one error coming in and the error correction procedure has 0 faults. So you say S greater than R or less than R?
Smaller.
Smaller than R. Yeah, okay. But so you want it to work in both situations. So you want it to work if there's one error coming in and no faults in the procedure, but you also want it to work if there's no errors coming in and there's one fault in the procedure. Right? You don't want that to change the logical state. Right? Because so the general ethos of fault tolerance is that if there's kind of a low enough density of errors, say only 1 per gadget, then the code should be able to correct it, right? And in particular, we don't want one fault somewhere to cause 2 errors in a code block. Okay? And that could be true in gate gadgets, it could be true in preparation, measurement gadgets, and it could also be true in the error correction gadgets.
It's just for me, after the state undergoes error correction with S false, it means that we lost kind of some information, and then when we will filter it through this thing.
Yeah. So I haven't told you how to do a fault-tolerant error correction gadget yet. We'll get to that in a little bit. But the point is we want to design it in such a way that there's enough robustness in the error correction procedure that even if one of the gates in the procedure goes wrong, we're still doing the error correction overall correctly. Maybe with the addition of one error into the state. One physical qubit error, which is correctable. Yeah?
In the ECRP property, are we assuming that on the left, the incoming state has at most T errors?
No, we're not assuming that because we want the error correction procedure to take an arbitrary state and correct it back to something that's close to a code word. Okay? So even if there's many, many errors here, we want this to work. That's how this ECRP is different from all these other propagation properties.
So if the state on the left has way too many errors and the state on the right will still be bad?
No. Well, depends what you mean by bad. So consider the case where S is equal to 0. Okay? So the error correction procedure itself has no faults. So if the state on the left has many, many errors, then the state on the right will be a valid code word. Now, it might be the wrong valid code word. Okay? This property here says nothing about that. That's what this one is for. Okay? But it will still be a valid code word. Yeah?
So for that ECCP, do we need R plus S to be less than T, or just R and S separately smaller?
No, we really need R plus S to be less than or equal to T. And the reason for that is, remember up here I said, well, what if the S faults are right at the end of the procedure? We can't correct those. But here, what if the S faults are right at the beginning of the procedure? Right? We had R errors coming in, and we have S faults right away, causing S more errors. And we still need to be able to correct that with our error correction procedure. So we need that R plus S is below the ability of the code to correct errors. So less than or equal to T.
But we already know, like, after that ECS, if we add a filter of S errors, it will not change our state.
That's at the end of the procedure. At the beginning of the procedure, we can't put an S filter in here. Well, okay. The point is that that this error correction procedure as a whole is supposed to correct the pre-existing errors. It doesn't actually have to work exactly that way, but early on in the procedure, it might not have done that yet. Okay.
Yeah. So I mean, like after that ECS, if we add a filter to filter out just the state of S, keep the state with just S errors, then we have that ideal decoder. If we have S, so if S is less than or equal to T, then that state will not be changed. Like
Yeah, that's after the error correction procedure. That's right. But that doesn't exclude that if there were a bunch of errors here and a bunch of errors here, the logical state changed. The error correction procedure might have corrected it to the wrong logical state in that circumstance when R plus S is too large. Okay, it will still be close to a code word, but it will be the wrong code word. And for the correctness property, that we care about that. Okay? Once I show you a fault-tolerant error correction procedure, maybe we can come back and see if it makes sense there. Any other questions?
So the definition of the ECS is that you error correct, you get the code word, but you have at most S errors.
Sorry, the ECRP?
No, the gate, EC and S. The error correcting with S errors. It means that you get close to a code word up to at most S errors.
Yeah, that's what the ECRP says. That if you have an error correction gadget with S faults in it, that you're close to a code word with S errors in it. Any other questions? Okay, so then let's move on to see some more examples of fault-tolerant gadgets. So we've already seen the transversal gates. Maybe it's worth commenting how the transversal gates satisfy these. So if you have a transversal gate, it satisfies very, very straightforwardly the propagation properties. That's kind of how we designed the notion of transversal gate. If it's just a single block, that means that it's just a tensor product of single qubit gates, and so errors can't propagate at all. So the number of errors we have is certainly the number of pre-existing errors plus the new errors that occurred during the gate. And if we have a 2-qubit block, well, they can propagate between corresponding qubits in different blocks, but they can't propagate within the same block. So we'll get this. The correctness property is a little trickier, but there you can see that because the errors won't accumulate. So let's again think of the single block case. So you start out with R errors. So you have some number of qubits. R of them might have errors in them, and we do this transversal gate that might have S more faults. So now we have at most T errors because R plus S is less than or equal to T. But the error correction procedure will correct those, right, when we do the ideal decoder. Okay? So then we'll get back to the same code word we had without the R errors, the code word we should have had going into this gadget. And similarly, if we if we decode it immediately, we'll get the same thing. Okay, and then the gate will do what it's supposed to do. Okay?
Why do you say immediately?
Sorry, I'm talking about the left-hand side where we do the gate gadget and then decode versus the right-hand side where we decode right away and then do the gate. Okay? But to make sure it's the right gate, of course, that's the stuff we were doing yesterday where we said, well, what is the logical gate? What's it doing to the logical operators, for instance? Okay, so the next thing I want to talk about is measurement. So this is really in the service of doing. Okay, so let's actually go to measurement for CSS codes. Okay, so for CSS code, how do I make a fault-tolerant measurement? That turns out to be pretty simple. So CSS code, you remember, had generators that were all X's from one classical code and generators that were all Z's from another classical code. So the Z's tell you that the state of the code will satisfy all the parity checks of that classical code C2. In other words, it's got to be a superposition of code words from the classical code C2. Right? Because if you think of it as a superposition of basis states that don't satisfy those parity checks will not give you the right eigenvalue. They'll give you -1 for at least one of those generators. Okay? So the CSS code has the form where the logical states are superpositions over over some code words of C2. And moreover, so we had C1 perp is a subset of C2. So there were two codes. Remember, we had this condition. And so it turns out, if you work it out, that the X's will take you between different code words of C1 perp. And so what we're going to do is we're going to sum over W in C1 perp, and U is some element of C2 mod C1 perp. And so if you work it out, this is what the code words of a CSS code look like. They're superpositions, uniform, these are the basis code words, I should say, logical code words. They're uniform superpositions of code words of C2, but only within the subset of C2 that's, that differ by elements of C1 perp. Okay? And so if we have such a code word, let's suppose for the moment that there's no errors. Okay? And you measure every qubit of this. It's basically a transversal measurement. Well, what do you get? You're going to get some random value of W. Right? W plus U. And that's a classical code word in C2. But by doing some linear algebra, you can figure out which coset of C1 perp it is. Right? You can say, oh, is this in C1 perp? In that case, I have the logical 0 state. Is it C1 perp plus some other particular vector that's in C2 but not in C1? Then it's that logical state. So in the case of the 7-qubit code, for instance, the logical 0 is the code words of so the C1 perp is the even code words, even weight code words in the Hamming code. And then that's the logical 0 is a superposition over all the even weight code words. And the logical 1 is then the superposition over all the odd weight code words in the Hamming code. Okay? And so by just, in that case, looking at the parity of the weight, you can tell whether it's a logical 0 or a logical 1. Okay? The main point here is that we've taken the code words of C2 and divided them up into different subsets. And by looking at which subset we're in, we can tell what the logical qubit was going to be when we measured in that basis. Okay? So now let's look what happens if there's errors in this state ahead of time. Well, if there's phase errors, that's not going to affect anything, right? Phase, because we're making a z measurement. The phase errors will change the phases, but that gets forgotten when we do the measurement. So all we care about is bit flip errors. And suppose we have bit flip errors. So I'm going to say xe is bit flips on qubits where e is 1. And so then the state XEU will be a superposition over W in C1 perp of W plus U plus E. Okay? And so then when we measure each qubit individually, we'll get W plus U plus E. Now remember, we have this, so this thing here is in C2, and this is an error. And so remember, in the classical coding theory, if we had a state that was a code word plus an error, well, we could identify what the error was by using the parity check matrix, right, to measure the error syndrome. And this is a classical code word, so we can do the same thing here, right? So after doing this measurement, we apply the classical error correction procedure. We can figure out where E is. Yeah. And get rid of it. And then we're left with one of these code words of C2. And then we just have to figure out which coset C2 mod C1 perp we have. Okay? So in other words, for CSS codes, transversal measurement is gonna solve our problems. So how does that satisfy the measurement? So there's no measurement propagation property. We just have a measurement correctness property. So suppose we have a state with R errors in it, and we have a measurement that has S faults in it. Well, that means that this E here should incorporate not just the pre-existing errors, but any measurement errors we have as well. Since we're measuring each qubit individually, S faults means that S of those single qubit measurements might be wrong, right? And that would cause the output to have bit flip as well. And so E just has to incorporate both of those, and then all of this will go through. Okay? Any questions on that? Okay, so so now let's do error correction for CSS codes. So this procedure that I'm going to show you is known as Steen error correction. So in Steen error correction, we're going to build on this measurement procedure, and the way we're going to do it is we're going to think about, suppose instead of doing a destructive measurement like this, we want to do a non-destructive measurement. I didn't write down for you what the gadget properties, fault-tolerant gadget properties for that would be, but you can still imagine coming up with a fault-tolerant procedure. So suppose we have a code block here, and we want to do a non-destructive measurement on it. What would we do? Well, if it was an unencoded qubit, we could take an ancilla qubit in the state 0 and do a C0 gate, and then measure the ancilla. And of course, for an encoded qubit, we can do the same thing. It's because we could do all of this with fault-tolerant gadgets. So this will be a logical 0. So we have to create somehow a logical encoded 0. I haven't shown you how to do that yet. But then we do a fault-tolerant C0 gate, say a transversal C0 gate, and then we measure destructively the ancilla, right? And clearly this is also a measurement of the logical state here, right? But in this procedure here, let's look what happens when there are errors. So there might be some errors at this point, right, when we prepared the state, and certainly those will show up here. There might be some errors in the C0 gate. Those could also show up here. There might be measurements in the error. That might those can show up here too. But moreover, there might be errors up here. What's going to happen to them? Well, if they're phase errors, if we're doing the transversal C0, they're just going to stay up here. They're not going to come down and affect our measurement at all. If there's bit flip errors up here, they'll get propagated through the C0, right? So for any qubit that has a bit flip error here, this qubit, the corresponding qubit down here, will acquire a bit flip error. And that will show up in our measurement as well. So the error we have here, suppose we have, let's see, errors E1, E2, E3, E4. And let's only think about bit flip errors. Well, the error in the measurement will be the sum of all of those. Now, if this is not too many, then we're still okay. We're still going to get the right logical measurement here. Okay? So that's good. But the thing I want to point out is that we have this E1 here. So when we do this procedure that I said here, and we decode this, and we do the classical, we measure when we do the classical decoding procedure where we figure out what the classical error is, we're actually learning some information about what the error was up here. I mean, it's all mixed up with errors here as well. but it's in there. Okay. So that's going to be the kind of the germ of the Steen error correction procedure. But you'll notice that by itself, this is a horrible error correction procedure. Why is that? Well, we've measured the logical state up here. We don't want our error correction procedure to change the logical state. We certainly don't want it to measure it. That would be totally destroy our computation. So let's change this a little bit so that we don't change the logical state up here. How can we do that? Well, suppose instead of a 0 ancilla here, we had a plus ancilla, 0 plus 1. And then we do this C naught here. Well, now we still have all the errors from here and here and here and here accumulating in this measurement. But if you do a C naught to a plus state, then this logical state doesn't change. Okay, and this logical state doesn't change either. Right, because a naught on a plus just gives you back a plus. Okay, so this thing has the same property where it's accumulating, and in particular propagating the error information down here, but it's not doing anything else. Right, it's only telling us about the errors that occurred in this, well, the pre-existing errors and the errors that occurred during this. Okay? And so that's what I want to use as my error correction procedure. But this is, of course, only correcting bit flip errors. So Steen says, well, we'll do that, and then we'll also do this in the opposite basis for phase errors. So for phase errors, we want to take a logical 0 as our ancilla, and we do the C naught the other way. And so when we measure these two things, we'll be getting information. So if we have bit flip errors up here, they'll propagate down here, and we'll see them here. If we have phase errors up here, well, they won't do anything here, but they'll propagate backwards through the C naught, and we'll see them here. Sorry, this is not right. This you need a Hadamard, because you want to turn those phase errors into bit flip errors so that you can see them in the measurement. Okay? And again, if there's no errors in this whole system, these C naught gates here don't do anything, because if you control a C naught with a 0, it doesn't do anything. But if there are errors, they propagate into the measurements, and you can see them. Now, of course, there's other things bad things that can happen here. So for instance, if you have phase errors down here, they'll propagate up here. That's actually not too bad, because then you'll see them here again. But if you have bit flip errors down here, they can propagate up here, and then you're not correcting them. So that's an example of the sort of errors that can occur kind of at the end of the procedure that you won't be able to correct during this procedure itself. Okay, so let's think a little bit about, so I would claim that this is a fault-tolerant procedure. And I'm not going to go through a complete proof of that, but let me give you kind of the sense of why it works. So first of all, let's think about the case. Well, this is kind of, we've already done the case where there's no faults in the procedure. There's just pre-existing errors, right? In that case, the bit flip errors get propagated down here, and that's the only source of bit flip errors. So when we deduce, so I could say that what we're doing here is we're going to take these pieces of information, and we're going to figure out a bit flip error and a phase error and use it to correct the state. Okay? So in the case where there's no faults in the procedure, this works fine, right? The bit flip errors get propagated down here. We see them. We correct them. The phase errors end up here. We see them. We correct them. Yeah?
We're measuring stabilizers, right?
This is for a CSS code, which is a stabilizer code. We're not directly measuring the stabilizer eigenvalues, but you can deduce that from this information that I've done. Okay? These are here are code words of the same CSS code. So one way to think about it, if you want to think about measuring the stabilizers, so what we've done here, well, So what we did here is we measured transversally, right? We're measuring z on every qubit. And once you have z on every qubit, you can multiply them together to find the eigenvalues of the z stabilizer generators. And so here it's kind of the same thing, because the bit flip errors propagate forward. And so what you're measuring here is the eigenvalues of the z stabilizers for this thing after the C0 gate, for this thing here, okay, which kind of combines the eigenvalues of the z things here and the z things here. And then this down here is measuring kind of the physical x's. You can put them together to get the x generators of this thing. And that combines the x generators eigenvalues here with the x generator eigenvalues here. So it's in there that you're measuring stabilizer generators, but you're not doing it kind of explicitly. Any other questions? Okay, so let's see. So what about the ECCP? Why is this correct? Why does this not change the state? Well, we discussed that already too, right? If there's not too many errors anywhere in this procedure, well, okay, I guess we didn't completely do it, but if there's not too many errors anywhere in this procedure, certainly errors can accumulate at various points. But we're not, if the number of errors is small, remember, these logical gates are not changing the state of the encoded qubit. So the remaining part of the ECRP and the ECCP, that's a little more subtle. So what happens if there's some errors in the system that are propagating in weird ways? So the errors that propagate from here to here, that's not bad, that's under control. The things that we have to worry about that probably are worrying you right now is, well, I said the errors here are a combination of things that happened up here with things that happened in here and in here and in the measurement itself, right? So some of these errors that I'm correcting might not actually be in the code word. So I could actually be introducing errors when I do this, right? If there's an error, a bit flip error down here, it doesn't propagate up. We see it in the measurement. We think it came from here. And so we try to correct it, but it wasn't there. So we're actually introducing a new error. That can definitely happen, okay? But it's all under control, right? The number of new errors that we introduce that way is at most the errors that occurred in this preparation and maybe this gate and maybe this measurement and this preparation and these gates and this measurement. So all of this is within inside this EC box, this fault-tolerant EC box. Okay, so there's at most S faults in this whole thing. And so these extra errors that we introduce, there's at most S of them. Okay? And the other thing that's a little tricky is that you could have errors that propagate up here and also come in here from measurement, but those turn out to be on the same qubit, so it doesn't actually matter. So the upshot is that whatever pre-existing errors come in, we correct them. We might also be introducing new errors from errors that occurred in the system, or that errors that we mistakenly think came from the system but actually came from, say, the ancilla. But that's all that this ECRP is saying. It's saying that the pre-existing errors are corrected, but any new errors that occurred in the block, they might still be there. Okay? Or they might get introduced as part of the procedure. Okay? Does that make sense? So are there any questions on that? Yeah.
So the errors that might be introduced in this error, like for example, it doesn't bit flip, then it would have to be like a bit flip on the logical, not many.
Sorry. So we can distinguish between bit flips on the physical qubits and bit flips on the logical qubits. So when I'm talking about S faults, I mean, I haven't told you how to make these logical states yet, but when I'm talking about S faults, I mean S faults on physical qubits. So there's only producing errors on S physical qubits. If there's an error on a logical qubit at any point during this procedure, then sure, this whole thing will fail. But to get an error on a logical qubit requires, d errors, where d is the distance of the code. Any other questions? Yeah.
Can you do an example of an error correction that is bad? That actually doesn't follow ECC?
Sure. Okay. So, so here's kind of, so for any stabilizer code, there's a pretty straightforward non-fault tolerant way to measure the bits of the error synchrome. So if you have a generator that's like, well, let's say ZZZZ, and then tensor i's, like in the 7-qubit code. So what we're going to do is we're going to take one ancilla, and we're going to start it in the plus state, 0 plus 1, and we're going to do controlled Z operations to each of these 4 qubits. And of course, the other qubits in the code block we can ignore because they're not involved. So what does this do? Well, if we have a state with eigenvalue plus 1, well, every time we do a controlled Z, if that state is a 0, nothing happens. If that state is a 1, we get a phase of minus 1, right? Which will change the phase of this plus state. Right? We only get it when this qubit is 1. So we're kind of kicking back that phase. And so if we have a state of even parity, we'll flip the phase an even number of times. If we have a state of odd parity, we'll flip it an odd number of times. So this will be plus if the eigenvalue is plus 1 and minus if the eigenvalue is minus 1. So we then do the Hadamard transform and we measure it. Okay? So this procedure here is a way to measure the eigenvalue of ZZZ. And you can see that you can generalize this for any Pauli, right? You just put the appropriate Paulis in here. But it's not fault tolerant. So why is it not fault tolerant? Well, suppose we have a bit flip error that occurs here. Well, that will propagate forward along this controlled Z gate. So this is 1 when it's supposed to be 0 and 0 when it's supposed to be 1. And so that'll create a Z error here. And it'll also create a Z error here. Okay? So this error has propagated into 2 errors. So even if everything was perfect to start with over here, one fault has caused 2 errors. And that's bad. So that's an example of the failure of ECRP. There's other problems with the procedure. I mean, suppose you have an error here that causes this measurement to be wrong. Well, now you think the error syndrome is one thing when it's actually something else. And that can cause you to do the wrong correction later. That can be very bad. So there's ways of fixing this up. You use a more complicated ancilla called the cat state, 0, 0, 0, 0 plus 1, 1, 1, 1. And then you have to repeat these measurements. So this is kind of, and once you do that, then it becomes fault tolerant. That's known as Shor error correction. It's more complicated, but it works for any stabilizer code. But in a lot of cases, this one is better. Now, I should say for the surface codes, people actually frequently do this anyway, even this non-fault tolerant thing. But they do repeat the synchrome measurement. And they just live with the fact that there's 2 errors that propagate, because it's only 2 errors. Right? And so if you have a big surface code, you can tolerate a little bit of blow up from 1 fault to 2 errors. You just don't want too much. So that's kind of a weaker form of fault tolerance. Yeah?
Do we further correct the new errors we added in Steam code?
Not in this particular error correction procedure. But remember, this is part of a bigger circuit. where we do some gate gadget, then we do error correction, we do another gate gadget, we do more error correction. And so any errors that we introduced into this thing here, they'll stick around, and we'll get them the next time we do error correction, provided there aren't too many more errors that occur in the meantime. So you have to worry about that. So another option, of course, is to repeat this procedure right away. And then you're more likely to correct those errors. Of course, then it's also possible that that thing could introduce new errors. So you can't ever completely avoid this thing. But if you don't do the correction until you've repeated twice and gotten the same thing, then you can be pretty confident that it's right.
And is there no way to distinguish whether we introduced the error or it was already there?
Yeah, well, the way to do it is to repeat this procedure right away. So you don't do this part. You just do this twice, say. Right? And if you get the same error both times, then it's pretty likely it was already there. It could be that the same thing just happened twice. That's possible, but that's less likely. And that would require 2 faults rather than just 1 fault. But the cost of doing that is you're adding more gates, and those gates can have errors as well. And so it turns out it's usually better just to do it once. Even though you're introducing more errors, the trade-off of adding more gates makes it probably not worth it. I don't think that's been totally fully studied carefully. But that's in the proofs. That's the way it seems like it works. Any other questions? Okay, so right, running out of time. Okay, so let me tell you how to do the fault-tolerant state preparation. And the answer, well, okay, so what about non-fault tolerant state preparation? Suppose I have, where did my purple go? Suppose I start out, so how do I make logical 0 state without worrying about errors at all? So I'm not going to tell you how to do that in detail, but you'll start with 7, in this case, physical qubits. 1, 2, 3, 4, 5, 6, 7. And then you do some circuit, some big circuit, and you'll get out 7 physical qubits that are supposed to encode a logical 0 state. Okay? You can work it out for whatever code you're interested in. But this procedure will necessarily involve C0s between 2 qubits in the same block. So it's never going to be fault tolerant by itself. Well, the original thing that you come up with is not going to be fault tolerant by itself. So that's a problem, right? So in order to satisfy our needs up there, and really to satisfy these the PPP and the PCP, we have to be a little more careful. But the thing is that this thing here is supposed to be a logical 0 state. So we know what it's supposed to be. This is a much better situation to be in than when we have some code block in the middle of a quantum error correcting code where we don't know what it's supposed to be. So what we're going to do, well, one way we can make this fault tolerant is we can take 2 of these things, or even 3 if you want, and do this non-destructive measurement. Okay? So remember what this tells us. So when we measure here, we get information about the combined error of single qubit bit flip errors on both of these put together. Okay? And we also learn something about the logical state. We learn if the logical state is 0 or not. Now, of course, there's all sorts of things that could go wrong here. So suppose we have up here a logical 1. Then we'll see here we have, but this is still logical 0. Then we have here a logical 1 when we do this measurement. And that will detect and we'll say, oh, that's wrong. Let's throw it out. Now it could also be that down here we have a logical 1, and up here we have a logical 0. In that case, we'll also see a logical 1 out here, and we'll throw it out when we didn't have to. But that's okay. If we want to just be safe, we'll only keep it when we see a logical 0 down here. And so what if we throw out states that would have been okay sometimes? So long as the states that we keep are right, we're happy. So in order to have a problem, we would need a logical 1 up here and a logical 1 down here. That's not the only way we could have a problem, but that's one way. A logical 1, we could get a logical 1 with just one fault over here. So that would be bad. But to get a logical 1 up here and a logical 1 down here, these are separate encoding procedures. So we need two faults. Okay? So if our code corrects one error, that would be outside the purview of the, I guess this is the PCP, because we have two faults and t is only 1. So that would be acceptable. Now, another bad thing that could happen is we could have, well, in general, for the 7-qubit code, this doesn't happen. But in general, we could have, say, 2 single-qubit errors up here out of one fault. But maybe it doesn't change the logical state for whatever reason. Well, that would be bad too, but that's something we can then correct down here, because we'll see those 2 single-qubit errors that accumulate down here. Now, again, we could have a situation where there's actually 2 down here, and we would have been OK. We're unlikely to see 1 up here and 1 up here, because that would require faults both here and here. Actually, what's more serious is if you get 2 up here and 2 down here, and they cancel each other. So then you don't see any errors down here. But again, we're not too worried about that, because that requires a fault up here and a fault down here. OK? Now, this, of course, doesn't tell you anything about phase errors. There's no logical phase error on the 0, so we don't really have to worry about that. For some codes, you would have to worry about having 2 physical phase errors here. For the 7-qubit code, it turns out that's not a problem. Let's see. So, but if you have a bigger code or a different code where it is a problem, you can then add on a second step where you make a logical plus here, and you do the C0 the other way and measure. So it looks a lot like this Steen error correction procedure, but with the opposite ancillas. Okay? And the upshot is that if it passes both of these measurement tests, well, it's pretty likely that the state is correct. And in particular, it will satisfy the PPP and the PCP. Okay? So let's see. So this is to make a logical 0. If you want to make a logical 1, you can just do your Hadamard gate, logical Hadamard gate. And in fact, this is good enough to stick this thing into these error correction steps. Okay? And so we're going to make, we don't actually need to do this for the error correction because, well, okay, it depends on the code. For the 7-qubit code, we don't need to do it. And so that will all become part of this big error correction gadget. So error correction is a pretty big, complicated gadget, certainly much more complicated than the transversal gates that we've seen so far. Okay? Any questions about that? Okay, so now we've done state preparation gadgets, we've done measurement gadgets, we've done error correction gadgets. We have transversal gate gadgets for the 7-qubit code for all the Clifford group, but that's still, unfortunately, not a universal set of gates. So how do we complete the universal set of gates? It turns out that if you take the Clifford group plus any gate outside the Clifford group, that is a universal set of gates. There's only a finite number of gates, but when you multiply them together in different orders, you can, since they don't commute with each other, you can get arbitrarily small rotations. Okay, and use that to generate anything that's close to any unitary, logical unitary. So we need some gate outside of the Clifford group. And so the gate I want to use is going to be what's sometimes called the t gate, but I like to write the r pi over 8 gate, and that's e to the minus I pi over 8, e to the plus I pi over 8. So it's a rotation about the z-axis. And you'll see why I want to do this in a minute. So, so the way I'm going to do these gates is, again, it's going to involve some state preparation and quantum teleportation. So what does quantum teleportation look like? So now forget about error-correcting codes for a bit. So quantum teleportation, you create a Bell state, 0, 0, plus 1, 1. You have Alice up here, has some state psi. She makes a Bell measurement, gets 2 classical bits, and then based on those classical bits, she sends them to Bob, who does a poly. And then Bob outputs the state psi. I'm going to need a little more space here. Okay, so suppose Alice and Bob are just next to each other in a quantum computer, and then Bob wants to do some gate U on this state after getting this teleported qubit. Well, when he does that, of course, the state that's out here is U psi. Okay, but maybe Bob is impatient, and he doesn't want to wait until Alice does her Bell measurement in order to do U. He decides he wants to do U earlier on this qubit. Well, can he do that? Well, he can, but now when he gets the classical bits from Alice, instead of doing a poly, or instead of doing this poly, he's going to have to first undo the U, do the poly, and then redo the U. And so we can incorporate that into one gate by saying it's UP U dagger that he's doing. So remember, the order is flipped in the circuit relative to when we normally write it. So this U dagger is canceling this U, and then he does P and then U. Remember, this is a combination that we've seen before. It's the conjugation of the poly. So for instance, if U is in the Clifford group, then this is another poly. Okay? And so what that means is that this is not any more difficult than it was for him to do the U afterwards, right? He still has to do a poly. He just has to change around the classical bits to figure out which poly he does. Okay? So for Clifford group gates, this is fine. And moreover, that means that instead of having to do U on this unknown state here, he can do it on a known state. Right? So instead of preparing 0, 0 plus 1, 1, they can prepare 0, 0 plus 1, 1 with U on the second qubit. Right? And they can do that ahead of time, and they know what state it's supposed to be. So, if it's hard to prepare, they can work at it. They can spend a lot of time doing that, checking it, whatever they need to do. And then Alice comes along with her qubit. She teleports, and Bob only has to do a poly when U is a Clifford group gate. Okay? But we want to go beyond Clifford group gates. So what we want is a situation where UPU dagger. So in the Clifford group, we could do this because UPU dagger was a poly. It was something simpler than this Clifford group gate that we were trying to do. And so more generally, we want to do a situation where UPU dagger is simpler than U. So in particular, I want to define a set of gates called C3, which has the following properties. So it's a set of U such that UPU dagger is in the Clifford group for all P in the poly group. Okay? So when UPU dagger is in the Clifford group, that sounds like something that's simpler than a gate that's outside the Clifford group. And it turns out that this R pi over 8 gate is in C3. You can work that out. You just have to calculate UX U dagger, Z U dagger. Well, UZ U dagger is just Z because it's a diagonal gate. You just have to calculate UX U dagger, and you'll see that it's actually related to the pi over 4 phase rotation with a bit flip as well. Okay, so that's why this is one of the gates that I want to pick. And so the way I'm going to do it, again, forgetting about error correction for a moment, is suppose I had just some physical system where I knew how to do Clifford group gates. I don't know, maybe it's Majorana fermions. That's actually a good example. But I don't know how to do anything outside of that. Well, if I can create this state with u being this pi/8 rotation, then I can do the Bell measurement, and then I just have to do some Clifford group gate to correct it, and then I've done the pi/8 on this logical state. Okay? Does everyone see that? Okay, so so this state here is called a magic state. And then this procedure is a magic state injection procedure. So we're creating a state that kind of already has the gate encapsulated in it, or at least the hard part of the gate, and then we inject it into the computation. Or maybe another way of thinking about it is we're injecting the computation into the state. It's kind of what the teleportation does. Okay? So how does this apply to fault tolerance? Well, we know how to fault tolerantly do a Bell measurement, right? That involves some Clifford group gates and some measurements. We know how to fault tolerantly do Clifford group gates. So suppose each of these lines is now a logical qubit, right? And we create the logical magic state. Zero, zero, plus 1, 1. With the u applied to it on the second qubit. Suppose we had some way of creating that logical magic state. Then we could do this whole procedure to do the logical pi/8 gate. Okay? Does everyone understand that?
So the whole goal is to apply it on a known state instead of unknown state.
Yeah, so that's what we've done, is we've shifted it to saying we only have to make this known state rather than applying this unitary on an unknown state. So that does seem like progress, right? It seems like it's something that should be easier, but of course it's not at all clear how to do that. So that's, since I'm out of time, that's something I'll talk about tomorrow. Okay? So once we learn how to make these magic states, that will be our, that will complete our fault-tolerant set of gates. We'll have a universal set of gates. So yeah, so let me give you a homework problem. So another, oh here. So this is actually different from the magic state that people most normally think about, and it's a little more complicated. It involves two logical qubits. So I want you to derive the kind of the normal pi/8 magic state involving one logical qubit, and here's how you'll do it. So here's a little circuit. This is a measurement. So you have an arbitrary qubit here, and I claim that if you run this circuit, you take a plus ancilla, you do a C0 measurement, and I believe it's an X conditioned on that, although I guess I didn't check that carefully, that you should get back the state psi down here. Okay, so part A of the exercise is show that this works. And then part B is use it to find a 1 qubit magic state and injection procedure for the pi/8 gate. Okay? So that's it for today. Thanks.
Use this pi/8 just because it has this nice property, or?
Yeah, that's right. So yeah, so really anything in C3 is going to work the same way. But you know, some other gates in C3 are multiple qubit gates, like the Toffoli gate.
Yeah.
and so that makes it more complicated because then you have to deal with more qubits. And in particular, fault-tolerant gadgets that involve multiple qubits, you have to worry about errors accumulating when they propagate. And so it's kind of best to minimize those when you can. So that's the main reason why the pi/8 is so popular. I mean, basically all the 1 qubit things in C3 that are not in the Clifford group are kind of equivalent to pi/8. Pi/8 about different axes.
Does C3 have any name, or it's just C3?
It's just called C3. So there's you can make a whole series of these things by saying that UP dagger. So if you're UP dagger in C3, that's the definition of C4, and so you can have CK conjugate, and so you can do these teleportation things in kind of a link, where you do one after another to get more and more complicated gates. You don't need to because this is already universal, but if you want to get it exactly, that's sometimes good, and that's called the Clifford hierarchy. So that has a name.
And in this whole discussion, we don't assume crosstalks.
That's right. Yeah. So this is the error model that I was talking about at the beginning, where if you have a fault in one location, there can be errors in the qubits involved in that location, but nowhere else. And the errors in that model are uncorrelated between different locations.
Yeah. But do we study with crosstalk also?
So I'll get to that a little bit tomorrow. So we can tolerate some correlations between errors in different locations with a limited amount. People haven't really carefully studied what the threshold, for instance, would be in that circumstance. And so there's a lot more that should be done, I think, to study that. But conceptually speaking, the same basic things work. I mean, so all of these things, I'm being very strict. I'm saying that one fault can only cause one error. But if one fault can cause 2 errors, you can tolerate that. You just need a code that corrects more errors, right? The real problem is if one fault can cause many, many errors and totally ruin your system.